Hello. So this is a continuation of the previous lecture where we were talking about interacting fermions. There we talked about what all possible interactions the fermion can have with variety of particles, and what is the modification of the Wick's theorem. Actually, Wick's theorem doesn't get modified. It's the rules of time ordered, normal ordered, and the contraction, they get modified. So let's all these things were done because we wanted to deal with an interacting theory, and the simplest interacting theory that involves fermion is a Yukawa model that has a scalar and the fermion. So let's start with the Yukawa model that has the Yukawa. This is Dirac. The Dirac part of the Lagrangian plus the Klein-Gordon part of the Lagrangian, and then the interaction piece. Some interaction piece. Let's write it explicitly. So I have psi bar I del slash minus m, that's my Dirac part, plus 1 by 2. Let's talk about the real scalar, del mu phi minus 1 by 2 m square phi square. Let me just write this is mf for saying that it is fermion mass, and m is the mass of the scalar. And then I add another term which is the coupling between the fermions. So these are all free theory. The first term corresponds to this term corresponds to the Dirac Lagrangian, this term corresponds to the Klein-Gordon Lagrangian, and these are the free theory that we already know. And even if I put the two theory in the same Lagrangian, that still remains two non-interacting theory, and both are separately solvable, exactly solvable, because they are free theory. And now what we do, we mix them using the scalar kind of coupling. So let the coupling strength be G, psi bar, psi, and phi. This is my Lagrangian density. Now we have already seen that the mass dimension of scalar field is 1. Okay, this is 1, this is 3 by 2, this is 3 by 2. So total it add to 4, so the mass dimension of G is 0. So G is a dimensionless quantity. So this is the strength of the coupling, and it is typically of order 1. And when I say G is small, what I mean is that G is much smaller than 1. I mean, smaller than 1 when I say it is small. Okay, so the smallness or largeness of this G, which is the Yukawa coupling, will decide whether the theory is perturbative or not, whether the perturbative interactions we can use here or not. Okay, so if this is the Lagrangian, then this is the potential term in the Lagrangian. That when write the Hamiltonian, so Hamiltonian will have, for this theory, sorry, let me just write the interacting Hamiltonian. Total Hamiltonian interacting is G times T3x psi bar x psi x phi of. Okay. So G times this term with a plus sign is the Hamiltonian density. If you integrate over all 3x, then you get the total Hamiltonian. Okay, so this is the thing, and what we need to discuss further is that in this theory we need to do computation of Green's function. Okay, so for example, let's just say I want to compute 2-point Green's function. So this is time ordered product of psi x psi bar y. Okay, this I want to compute, and using the general formula as discussed in previous lecture and also discussed in QFT1 course, that this is going to be related to the time ordered product of psi bar x, sorry, there is no bar on psi, psi x psi bar y, then exponential minus I d4x, and in this particular case I have this g sitting over here, psi bar x psi x psi x. Okay, this is, I'm just substituting the interaction Hamiltonian in the interaction picture. So all the psi's appearing on the right hand side are the interaction picture guy, and all the psi's appearing on the left hand side are the Heisenberg picture guy. So I'm writing the Heisenberg thing explicitly, but whenever I'm not writing anything, that means it is the interaction picture guy. And this is divided by 0 time order product of exponential of minus I g d4x psi bar psi phi, all function of x. So this is what we have. Now, in order to compute this, I need to compute the numerator and the denominator explicitly, order by order. Okay, so I will come to the details of the diagrammatic way of doing it. You have already had some exposure of the Feynman diagram in the previous course of KFT1, so we'll eventually going to use it, but I want to do for the first time in slight more detail without using the diagrams, or rather using the diagrams to the least, only to suggestively indicate what terms there are, and see where all we need to be careful when dealing with the fermions. So what we do, let's look at the numerator and do the expansion of this exponential over here. Okay, so if I write the numerator of that thing, the numerator is equal to 0. The very first term is this identity, so time order product of psi of x psi bar of y, okay, followed by I times g minus I times g, I should say, and some d4z, okay, will come, and then the time order, then the vacuum expectation value of time order product of psi of x psi bar of y, and the term that is coming from the Hamiltonian, I already wrote minus ig and d4z over there. So what is coming is psi bar z psi z phi z 0. Okay, then the next term in the expansion would be minus I g squared by 2 factorial, which is equal to 2 d4z d4w, because the two insertions of Hamiltonian, then 0 the time ordered product of psi of x psi bar of phi, and then comes psi bar of z psi of z phi of z multiplied by psi bar of w psi of w phi of w, curly bracket close, 0 plus so on. Okay, so I need to compute the vacuum expectation value of the time ordered product of this guy. So first term, the very first term in the numerator is nothing but the propagator, right? So that's trivial. So this is nothing but psi of x psi bar of y contracted, right? So when I have a time ordered product, that can be written as normal order product plus the contraction. There's only one contraction happens, so all the pairwise contraction we have to consider, and the vacuum expectation value will be non-zero only in those terms where there is all the terms are pairwise contracted. Okay, because if it is not, then there will be some operator in the normal order, and those normal order operator will always kill the vacuum, so that will contribute 0. Okay, so this first term have this thing pairwise contracted, and this is gives me the propagator written by S Feynman propagator x minus y. Okay, that's my first term. So let's look at the second term. The second term I can contract the fermion fields in several ways. Okay, but let's not jump into that. Let's look at the scalar field. There is only one scalar field, and it cannot be contracted because it doesn't have, we need the two scalar field to contract it. So this fermion pair, whichever way we contract, the scalar remains uncontracted and normal ordered, and that kills the vacuum. So because of this unpaired guy, this will be equal to 0. Maybe I should write that in a different color. Okay, because of this guy over here, this leads to 0. Okay, field is not 0, is a vacuum expectation value of that will be 0. And the first non-zero contribution at a higher order will come from the second order. Okay, and in the second order, now we can say, how do I contract? It talks about all possible contraction. Okay, so let's talk about second order term in the numerator. So this is the guy, and what we know for sure is that the scalar contracts with the scalar. So what I have, so here what I will do the perhaps the cheap thing. Okay, so let me not do that quite yet. So this particular string of operators that you see, scalars and fermions definitely commute, so I can just take them across. They completely belong to different Fock space. There is not an issue. We can put it together, or all the bosons I can keep it together, and fermions maintain the order. Okay, so what I get, let's maintain the order. One of the possibility, so there's going to be several possibilities over here. One of the possibility is that psi x and psi y contract. Okay, so that leads to this particular diagram. So this is my x and this is my y. Okay, I'm writing diagrammatically. Let me not do that. Okay, so what I do, psi x, psi bar y contracted. Okay, and of course phi z and phi w contracted. Now what options do I have? Look at here. So at z, at point z, I have one psi bar and one psi, and point w I have one psi bar and one psi, and we know that psi bar and psi has to contract together. So what I do, I contract, so I take this psi bar z all across to the right hand side, and it gives me a minus sign overall because it goes across 3, so 1, 2 and 3 of these guys, or let me just keep the order same, psi bar z, psi z, psi bar w, psi w, and the contractions are of this kind. Let me just write the contraction without changing the sign or anything. Okay, these are the pair of 3 fermionic contractions and 1 bosonic contraction that gives me this. If I have to represent this by diagram, okay, so this is my x to y. Since the fermion, I will always use the arrow from the non how do I say, the arrow will always flow from psi to psi bar. Okay, if this is the convention used, then this is the guy, and then here is my z, and here is my w. Then z and w are connected by this scalar, and then there is a fermionic line from z to w. Okay, this is this guy, and there is another fermionic line from w to z. So there is kind of a fermionic loop. Okay, we'll see later that whenever there is a fermionic loop, the overall sign will always be a negative number. Okay, so there is a loop factor that you call it. Okay, so this is one possible diagram that I have, and as you can see, it is the expression for this diagram is this propagator multiplied by this diagram, and not to forget that this has a prefactor. What is a prefactor? Minus ig square by 2 d4x, sorry, no x, d4z d4w. Okay, this is there. I have to integrate the w and z because they are dummy variables. Now I can actually swap this. Wait a moment, that's not required. So this is just a unique answer. Yeah, I'm sorry, this is the unique answer. So this is in the second order term. This is one possibility, because the Wick's theorem says what is the time order product? All possible contractions. This is one possible contraction. Okay, so now let's look at another possible contraction where I say that x and y, the two external fields that were there, they are not contracting with each other. They are necessarily contracting with something else. Okay, the first step would be that both of them contract to a same vortex. Okay, so again the possibility over there would be minus ig whole square by 2 d4z d4w, and here is my psi of x, psi bar of y, and let me write the scalar later, and psi bar of z, psi of z, psi bar of omega w, and psi of w. Okay, there's a phi of z and phi of w which is contracted with each other. So let me say both x and y gets contracted with z in this example. So I'm gonna have contraction of psi to the psi bar and this psi bar. Okay, this contraction happened and this contraction happened like this. So diagrammatically speaking, again there is a point called this I could call it z. From there is a point called w. Okay, and the propagator from w goes back to w, and again you see it is psi bar to the right and psi to the psi bar to the left and psi to the right. I need to change the order to write it properly. Okay, so that will be give me a minus sign because it will be a trace of a matrix. Psi bar times psi is a number, it is not a matrix, while the propagator is supposed to be a matrix. So that usually the contraction rule goes that psi is to the right and psi bar to the left. Okay, so here you can see this psi x and psi bar z, they are in the correct order, but the other one has to change the position to get into the matrix. Okay, good. And that changing the position will make the psi bar go 2 spaces across, so there is no sign change, and the psi x and psi bar z will come next to each other by removing psi bar y across psi bar psi of z. Okay, so that's just one guy moving that we have to do. Now what is happening over there? So psi x, if this is x, from x to y, for x to z there is a link, and from z to, so this is x and this is z, from z to y, z to y, there's a link. So this is a diagram, which another way I can write, here is my x, here is my z, and here is my y, arrows flowing like this. Here is a scalar loop, a scalar lag, and here is the w is sitting there. And now here, this particular expression, if I write, I know that z and w are to be integrated out. So there is nothing special about which one is z and which one is w. But this is one possible contraction. Another possible contraction would happen that both x and y couple not to z but to w. So basically w and z are exchanged in role, and that is another diagram. So basically I have two diagrams of this kind. So this 1 by 2 that is sitting over there, if you see in the expansion, each of if I have nth order expansion. I have 1 over n factorial sitting over there, and if I can get the same diagram by permuting the vertices, or permutating which insertion of h is contracted with which one, if just I permute their names and get the same expression, that means I simply count it that many times. So this guy has to be multiplied by 2, not the first guy, because first guy there's nothing specific about w and z. They are contracting with each other, and the swapping doesn't make sense over here because psi x and y, the external guy, is not connecting to them, so they are not distinguishable any which way. Here in the second diagram they are distinguishable, but the final expression is same. Okay, now we move on to some more diagram where we demand that x and y, the two external guy, necessarily contract with different guy. Okay, so I have okay, minus I g squared by 2 t4z t4w, all the vacuum expectation value, blah blah blah. So one of the contraction pattern is psi x psi bar y. Let me write it first. Then psi bar z psi z, psi bar w psi w, phi z phi w. Of course this contracted with each other. There was a phi like here also, yeah, so I did not miss it. Let's say x contracts with z. Okay, then y contracts with w. Okay, then I have no option left, but this z has to contract with this w. This is the contraction patterns. Okay, so let me write it here. If I shuffle, what do I need? If I just put this psi bar y 1 2 3 4 across to this side, then this becomes simple. This is psi x and psi bar z comes next to each other, psi z and psi bar w comes to next to each other, and psi bar w, psi w and psi bar y comes next to each other. So everything is matrix, very nicely done, not an issue. No over on side change because psi bar y going across all of these guys. Okay, so diagrammatically I'm going to write, is my x followed by x is connected to z, so just write z. Now z is connected to w, so write w, and w is connected to y, write y. So fermion is flowing very nicely in this direction, and there is a scalar coupling between w and z. Okay, now this diagram also, if I swap w and z, if it is swapped, there is another diagram. Okay, so that leads to multiplying by 2 because expressions wise exactly remains same. W and z is a quantity that is integrated out, so there is no dependence on w and z, but I do have another way of another possible contraction where psi x contracts with psi bar w. Okay, so that will also be exactly the same. So let me just write that thing, that this psi contracts over there and psi bar contracts psi x, and it will have the same sign. You can just check it. Psi x psi bar y, psi bar z psi z, psi bar w psi w. So this guy couples with this guy, psi bar goes psi bar of x with this guy, and z with w is anyway was there. Okay, psi bar z, psi bar z, psi w. Okay, so again if I start with x, it will just rename these two guys and no change in the propagator happens. So psi x remains this, psi bar is just 1 2 3, 3 spots. If I bring to the left, psi bar W, 1 2 3 spots I am crossing it, so that's fine. And this is crossing 1 spot, so that is 4. And then this guy crossing 2 spots, so that is not same. So overall it's the same sign. Okay, you can just see that if I have to write exactly in the same sequence how many permutation I need, and that's the even permutation, so both of these terms will simply add up. Okay, good. Right, now okay, so that part is taken care of. So these are the kind of permutations, kind of contraction I can have. So roughly speaking, I can say x and y contracted with each other, the two external guy, x and y both contracted with the same vertex, and x and y both contracted with the different vertex. There are only 3 possibilities, and there are only 3 different kind of diagrams that will come from this thing, where the first diagram is just a product of free propagator with a bubble diagram. And note it, it's a 2-loop diagram. We'll come to the loop counting and all this later. And the second diagram is a tadpole diagram, where there is this fermionic loop which is connected to the another fermion leg by just this single propagator. If I cut this propagator, it falls into 2 pieces. So it has a certain topological property that it is not 1 point reducible, because I can reduce it into 2 diagrams by cutting a leg. This diagram, on the other hand, is 1 point irreducible. Okay, it's called 1 pi. 1 pi. Okay, 1 point irreducible diagram. So what is the meaning of this? If I cut the diagram at 1 point, so to say, if I cut one of the leg, does this diagram falls apart into 2 pieces? This one does not, but the example 2 does. It falls into 2 pieces if I cut at 1 point. And case 1, it's already into 2 pieces. Okay, so this is not even, it is certainly not irreducible. It is not even a 1 point irreducible. It's the second diagram which is a 1 point irreducible diagram. Okay, they have some important use we will come to later, just putting the name over here. Okay, so these are 3 kind of diagrams when I'm talking about the 2-point Green's function. Now let's look at 4-point Green's function. Okay, so 4-point Green's function, before writing over there, I'll say that again here I'm only doing the computation of the numerator. I'll do the denominator later and say what's the role of denominator, how the bubble diagram cancel out. Okay, so we'll come to that later, but first thing is that if I have 4-point Green's function, okay, so the 0th order, which means the identity from the exponential, will give me pairwise contraction, and the all other insertions, so odd number of insertions will give me odd number of phi, and all odd number of insertions will give me 0. The time order product will give me a normal order where the phi will hang around on unpaired phi, and that will give me 0. So only even orders will be non-zero for this 4-point Green's function. Okay, so if I'm looking for this time order product of psi 1, psi 2 bar, psi 3, psi 4 bar, and the first term in the numerator, okay, will be 0 time order product of psi 1, psi 2 bar, psi 3, psi 4 bar. And here already a certain thing that comes into place. So here what I can do, this particular guy, one of the terms, which is just the no interaction term. Okay, so let me use a notation to denote this, that expression for this particular full 4-point Green's function contains a term which is this. Okay, so that is the superset on the left hand side and a set on the right hand side, and this set is a set of terms which is written as psi 1, psi 2 bar, contracted, psi3 psi4 bar contracted, plus psi1 psi2 bar psi3 psi4 bar, where these two are contracted and these two are contracted. Okay, so let me write the second piece. So this is just psi1 psi2 bar contracted, psi3 psi4 bar contracted. So I'll bring this psi bar two places to the left, so it becomes psi1 psi4 bar contracted, and here psi2 has to go, so there's, since it crosses two pieces, no sign change, but psi bar has to go to the right hand side of psi3, so that becomes psi3 psi2 bar contracted. That gives me minus sign. Okay, so this minus sign is very important when I do all these permutations to put in the right order, proper order. So it's the product of two propagators. Okay, so this is a matrix, this is a matrix, here this is a matrix, this is a matrix. Just write down the product of propagators, and it's the difference between them which is a zeroth order term. So this is the very important difference that comes even in this first term itself. But when we go to the interaction terms, okay, so interaction terms mean when the higher order pieces, higher order Hamiltonians are, higher powers of Hamiltonians are inserted over here. So as we argued that the odd orders will not contribute, so 4.2nd order. Okay, so what that will be, minus I g whole square by 2 d4z t4w time order product. Okay, so let me write the full thing. 0 time order product of psi1 psi2 bar psi3 psi4 bar times all the everything outside I have written. So only thing that is left to write here is psi bar z psi z psi bar w psi w and phi z phi w. Okay, so this is the 4-point guy at second order, and here I have to find all possible contractions. Okay, so here again, this is the first term in the 4-point function that can possibly contribute to a scattering. Okay, and a way to see this, that one of among many terms that there will be. So let me just write those terms diagrammatically. So let me write first over here. So this is like 1 and 3, 1 goes to 2, this arrow, 3 goes to 4, this arrow. This was the first term, minus 1 goes to 4 and 3 goes to 2. This is the diagram. Okay, to diagrammatically I can write this expression like this. Now if I have to write something like this over here, I can still write when the contraction here is exactly in that way. So one of them is 1 2, other is 3 4, okay, multiplied by, this is z, this is w, I'm sorry, there is a scalar propagator, there is a fermion coming from here, fermion going like this. Okay, this is loop. One possible diagram is this. Then the another possible diagram will have this bubble thing multiplying the second piece, and again the minus sign will always be there. So whenever the contraction between psi1 and psi3 happens slightly differently than this one, there will be a minus sign appropriately counted. Okay, so this is when w and z guys contract with each other. So all these 4 guys do not connect to any one of the propagators. So that's one kind of thing. Other kind of thing, that these 2 guys connect to the propagator, one of the propagator. Okay, so what you have a diagram like, here is 1, here is either z or w, and here is 2, here is this guy, and here is this fermion thing multiplied by 3, 4. That's another set of, so this is one piece, this is another piece. These are all possibilities I'm writing. So these are still free propagation, right? So here the initial and final particle, I shouldn't say initial final, the 4 particles that we're talking about went into each other, didn't interact anywhere, and there was some vacuum fluctuation, it got multiplied with. Here there was some interaction in propagation of one of the guy, okay, but the second guy propagated as it is. And this I can keep on saying plus, but you know, you write plus or minus according to the sign of the diagram. And then there would be 1 going to 2, and here 1, 3 going to something, going to 4, and here fermion loop would be there. Plus there'll be 1 going to this, going to this, going to 2, 1 to 2 with this scalar loop, and 3 going to 4 as it is, this possibility, plus 1 going to 2 as it is, and 3 going to something, going to something, going to 4, this. Okay, of course all of this corresponds to 1 being connected to 2 and 3 being connected to 4, but I haven't considered 1 going connected to 4 and 3 being to 2. So a copy of all this for 1, 4 and 3 to pairing, copy for that. Okay, and all these diagrams that we are drawing is going to correspond to a non-interaction, means the 4 particles are not interacting together. The 4 particles we are talking about, they are always at least 2 components in the diagram. In the first diagram here, there are 3 components, the 2 propagator, 1, 2, 3, 4, and some bubble fluctuation. Here the correction of the propagator is happening in various ways, but still 2 independent propagators are there. So these are all corrections, contribution to the identity matrix in the S matrix, the scattering matrix. It is not the transition. Okay, the transition will happen only when all 4 guys, this diagram is a single piece diagram. So here we started with 3-piece diagram, we went on to 2-piece diagrams. Now continuing, okay, so let me just say continued here, and I'll get a diagram where, let's say, scalar is here at Z, this is here at, so this is connected by these 2 points are connected by scalar. 2 of the external guys connect to 1 and 2 of the external guys connect to another. Okay, let's just say 1 connect to Z, okay, and Z connected to, so this is Z, and here then yeah, so 3 connects to W and W connects to 4. Okay, so this is one of the diagram that is possible. Okay, and this is the first place you see the scattering amplitudes. Okay, but when you have to write this diagram, you have to be careful. What is the expression for this? Plus many more, but let me just focus on this diagram. So all possible contraction I haven't written. So what is this? Minus IG square by 2 d4z d4 omega, and what I have here is psi 1 psi bar z contracted, psi z psi 2 bar contracted, then I have psi 3 psi bar omega w contracted, and psi w psi bar 4 contracted, phi w and phi z contracted. I wrote in a different order, but that's all right. Okay, these many contractions has happened. So this is the expression for the diagram. Okay, plus since W and Z I could have chosen in any order, so this thing multiplied by 2 will always be there. Okay. Two pieces exactly will add up over here. Now one can again check by doing explicit ordering. So starting from whatever we had written, can I come to this combinations, and with W and Z exchange, can I get the same diagram, same connectivity between 1, 2 and all these things. Okay, of course there's a diagram where 1 and 4 are connected and 2 and 3 are connected. Okay, so that will be another diagram, but basically I'm writing one possible piece over here. This is contribution to scattering. Okay, and if I write this particular thing, if you like, you already saw, I'm sorry, you already saw in this expression over here that one is talking about psi1, psi2 bar, psi3, psi4 bar. Okay, and a time order product of this guy. Okay, but if I can choose in a scattering experiment, the time order is already chosen. Okay, so scattering, what is the time order is chosen? Starting from, so I have say 2 fermions going to 2 fermions. Then is the scattering that I'm doing, let's just say. Okay, so let me just draw a line over here and let's talk about the scattering thing. Let's just say a fermion, okay, in the initial state, I'm sorry, so I'm looking at fermion of momentum P plus fermion of momentum K going to fermion of momentum P prime plus a fermion of momentum K prime. Okay, this is initial state and this is final state. Of course it gives me a time ordering. Okay, so I have to first, in the scattering experiment, I have to first respect that time ordering. So what is the time ordering? So this initial state with momentum P and momentum K, if written in this particular order, this is up to whatever factor goes as A, P, Dirac, and I'm not writing the spinor index S to simplify the notation. Okay, this is acting on vacuum. Let's just say this is how I define the P and K. P coming to the left means it is the second particle. Okay, because the order matters. So here I have defined the initial state. Okay, if I swap them, the order will change. So this is a convention one has to choose. I chose this is my initial state, and this final state is also state. Okay, so P prime and K prime state is defined up to this some numerical factor as A P prime Dirac A K prime Dirac 0. So this is my initial state on the left hand side, this is my final state. So what is my transition amplitude? Okay, if I have to look at the transition T, so that is initial thing which is P K, final thing, okay, which is P prime K prime, defined as such. Okay, and something like S matrix over here. What is the S matrix? S matrix is nothing but this expression, this exponential thing, exponential Hamiltonian thing that we have been writing. That is will sit here. So to the leading order, they'll just connect to each other. Okay, and so let me just write this. This gives me P prime K prime final state. The complex conjugate of this goes as vacuum, and this guy goes into the reverse order, A K prime A P prime. Okay, so here some operators sit, here bunch of operators sit. So this can be given as the vacuum, and A K prime A P prime times whatever string of operator we have. We have A P Dirac A K Dagger, and this is by convention we write. Now what is this oval thing that I have drawn? It could be identity operator. In that case, this momentum has to match and the appropriate 2 propagators will appear, which is just this 1 going to 2 and 3 going to 4 kind of diagrams will come. Okay. Now if I put interaction and looking for this interaction of the diagram that is drawn in this page, okay, then what do I need is this psi bar psi and phi dagger phi, sorry, phi w and phi w and phi z insertions in between. Okay, so for this matrix element, if I have to write, so basically what I'm doing, I'm saying that the point 1 and point 2 and point 3 and point 4 has an identity. So point 1, let us say, is P momentum. Let me write it in a different color. Okay, let us say this is P, and it is not the right diagram to look at. Least not the way. Okay, so that's perfectly fine. P and K is here, and P prime and K prime is here. Time is flowing this way, the way arrow is drawn. Okay, I could have done from bottom to up also. So, but that would just say, so here particle 1 and particle 3 going to particle 2 and particle 4. That's just a convention. I'm just, in this particular example, I'm taking like that. Okay, so 2 fermions is going to 2 fermions is the interaction, is the scattering that we're looking for. It's not fermion bar, that's why I chose the time direction like that. Okay, so I have to write this. So 1 and 3 are the initial state particles. Okay, so if I have over here, this is 1 and this is 3, so they must be on the right hand side. Okay, and 2 and 4 must be on the left hand side. Okay, so here if I talk about the full contractions, then I don't have 1 and 1 2 3 4 is practically not there as a full fields. Instead of full fields, I only have A's and B's, actually A's and A daggers. So what I have, so what I need when I'm doing the contraction, okay, need to define what is a contraction, means psi of x, okay, acting on P and S. So here P vector and S spin full thing is written, and this contraction I need to define, and this is given by D3 P prime, let's just say 2 pi q 1 by square root of twice P prime sum over alpha. Actually there is no need of writing 2 terms. A P prime alpha u alpha P prime exponential minus I P prime dot x. This is acting on what is PS up to a factor. Well, that factor also, let me write EP AP S dagger. Okay, so this is what it comes out to be. Now I'm not writing the second piece in the expression of psi, because second piece is B dagger. Now B dagger and A dagger anti-commute, and both of them according to normal order will go to the left and kill the vacuum on the left. So that will not contribute. Only thing that will contribute is A and A dagger when I'm swapping the order. That's why I'm writing only this piece. Okay, so the second piece is irrelevant. So I need to, that's why I'm saying this contraction is a definition, because second piece, which is 0 or going to contribute to 0 eventually, that is not even written for saving the effort. So here of course you can just say that A P prime alpha A P S dagger can be written as minus of A P S dagger A P prime alpha plus 2 pi q delta 3 P prime minus P delta alpha S, right? This is the anti-commutator basically. Now once I put that in this swapped order, it becomes a normal order and it kills the vacuum to the right hand side. So this contributes to 0, It's important, this is not 0, it contributes 0 once acted on the vacuum. And there then I cancel all this energies and blah blah blah, okay, and perform the integral, and what I get is u s p exponential minus I p dot x acting on vacuum. Okay, so this is the meaning of this contraction that I get. Likewise, we can define that psi bar, if that acts onto the PS, okay, that is just V bar S P exponential I P dot x acting on vacuum. Okay, so this contraction will mean that. So if psi bar contracts with the initial state, it is basically antiparticle, creating an antiparticle in the initial state. I have an initial state with antiparticle, then it requires psi bar contracting with that initial state. Okay, so this is what I'm getting when a field contracts with another field, I get a propagator. When a field contracts with this initial particle state, I get the wave function. Okay, so when I'm writing this particular diagram corresponding to each initial and final state, I have the corresponding wave function. Okay, and for all the intermediate guys, I have the full propagators. Okay, so this is very important part of the Feynman rules, this guy and this guy, and it can have a conjugate also, that I have, pardon me, Ps as a final state, and of course if I have to derive it from this guy, I will have psi bar x contracting with that, and that will give me u bar s p exponential I p dot x, and I'm sorry, is 0 times this. Okay, and if I have ps, where p is the momentum, s is spin, psi of x acting on that, that will be sorry, the vacuum v of s p exponential minus I p dot x. Okay, so this is all the contraction rules with the vacuum. Now in the place in this particular place, when we had scalar, we only have the exponential factor. Okay, we didn't have these spinors. It is important to take care of the spinors or any polarization information for any particle other than spin 0, because it's going to have the corresponding polarization or the spin information when you contract the field with a single particle state. Okay, so this is a very important part of the Feynman rules. In the next lecture, we are going to discuss how we are going to draw the Feynman, we're going to actually complete the Feynman rules. We are going to do some graph theory thing, because the Feynman rules start with draw a diagram, and then we translate the diagram using the rules into an expression for the matrix element. Okay, now that is fine, but how do I draw the diagram? What are the guiding principles for drawing the diagram? That we'll also discuss hopefully in the next lecture. So here we stop for this part. So this is the second part of the interacting fermions. Then we go for the Feynman rules Yukawa theory, basically full Yukawa theory. Okay.